Thanks for the nice introduction and thanks for the invitation. So today I'm going to talk about quantum materials by design. So first, let's start with what is quantum materials, because all the materials can be quantum one way or other, but why we put these specific names for certain materials. So the definition of quantum materials is not well defined, but so far the experts are agree on this definition which says the material display quantum effect on macroscopic scales. They often shows very emergent and emergent phenomena. So for example, this is immediately remind you a superconductor, which shows the quantum effect in macroscopic scales. So now the question is how we can make these materials, or if they exist in nature, okay, that's fine, but can we make these materials in the laboratories, and how we design them. So this comes the second point where the design is. So which is basically we try to control certain parameters of the materials from the start, let's say exchange interactions or even lattices, geometries, or dimensionality of the materials. If you can control this in a very precise way, then we can produce very interesting materials. They have very interesting properties. So there's a two-way in our community to do this. So one is we call atom by atom, so we can control the position of atoms and then look at how electron behaves in that artificial lattices that we build. Other one is we use 2D materials. So we make heterostructures out of 2D materials. We combine different layers with different properties and then try to find some new materials that comes from the interaction between 2 layers or 3 layers. But the final property of the materials is probably do not exist when they are individual layers. So the tool, basically the tool that I am using is in two. One is the way we prepare the samples or grow the samples, where we use molecular beam epitaxy. So we have this type of ultra-high vacuum molecular beam epitaxy. Over there, we stack the materials layer by layer with atomically precise controlled environment. And later, we characterize our samples using so-called scanning tunneling microscope. So a few words about scanning tunneling microscope. So we have this type of metallic probe tip, and then we use this, we bring this tip very close to the surface, and then we scan. And using this technique, we can take images of the sample, and we can also perform spectroscopy. So we can look at how the local density of state looks like and how there are changes in space. So we have atomic resolution. So we have very high spatial resolution. And then the final function of the STM is you can also move things around the surface, which is called atom manipulation. And this is one of the function we use to construct this artificial lattices. But today I'm going to talk about something we use 2D materials, 2-dimensional materials to produce, which is so-called topological insulators. And this is basically class of superconducting materials, superconducting materials. They have a bulk, they have a superconducting gap in the bulk, but they have some metallic protected edge stays at the boundaries. And of course, there's a theoretical predictions, and this material might host Majorana fermions in theoretically it's possible, but as the previous speaker mentioned, there's still no smoking gun signature in experiment to prove this states actually host the Majorana modes, because in order to do this, one of the smoking gun experiment, you have to do this non-abelian statics, or what's called braiding operations. But so far, nobody demonstrated that, even if the Microsoft involved also, but there's no that experiment yet. But of course, you can learn very interesting physics by doing this type of artificial materials. So that's one of the examples I'm going to show in 20 minutes. So the first problem of this this topological superconductors is there's no natural occurring material, or there's some people are saying it might be topological superconductors like uranium telluride and some STO materials, but you can also achieve these materials artificial way by combining the SPU superconductors, conventional superconductor magnetism, and spin-orbit coupling. So in the end, you try to get this kind of engineered band structures. Now the next slide, I'm going to show how we can do this using this PowerPoint physics. So this is not actually theory, it's theoretical calculation. So apologize from the actual theory, guys. So we start with, let's say, simple parabolic band. Then we add spin-orbit coupling, which basically shifts your parabolic band, Lipse degeneracy, except one point where your Rashba spin-orbit coupling is 0. Now, when you apply or add a magnetic term, and then keep in mind the direction is perpendicular to the spin-orbit coupling, then you open a gap in there, which we call it magnetization gap, sometimes topological gap, and so on. But then, if you add superconductor, you basically duplicate the band in this way. Then another condition, in order to enter the topological phase, you have to put your chemical potential in the gap in here. So we have to have some kind of tuning or gating to tune your chemical potential to enter the topological regime. So schematically shown here, so you can have this type of regions where you have trivial states and you have topological states. So people have been trying this on various different systems. For example, one of the first example is by doing this self-assembled iron chains on lead surface. And what they observed is this, at the end of the chain, this localized states, which at the time is signature Majorana fermions. Later, people also tried more controlled measurements by positioning the atoms in atomically perfectly chains, and then over there they also claim to observe. They also see the end states in there too. Of course, this is now it's one-dimensional systems, but it's also predicted this can be observed in two-dimensional systems if you have ferromagnetic lattices on superconductors. And over there, it might be even interesting, some very rich topological properties you can observe. And people also try this in experiment by directly growing this type of ferromagnets on top of superconductors, or directly on top, or buried underneath. And all these cases, they observe this type of, in this case, it's not single states, but it's a 1D age mode that's traveling around at the edge of the ferromagnet. So now the question is, can we do this in 2D materials? So over there, for example, you have these van der Waals theta structures, which you can prepare it very well, and you can twist them and so on. You have more parameters to control. And today, so I'm going to focus on the same experiment, but in two different aspects. So what we do is we use this van der Waals superconductor, niobium diselenide. It's SPU superconductor. It has like 9 Kelvin or 7 Kelvin TC, and then we directly grow the ferromagnet, outer plane ferromagnet chromium bromide on top of this layer on superconductor using MBE. If everything checks out, then we should expect this age states, and we are trying to locate that using scanning tunneling microscope. So this is how it looks like when you grow chromium bromide directly on UHP, directly on these superconductors, and that's some samples that we get as STM image, and here's a magnification of some of the areas. And those patterns here is a Moret pattern, because here we don't have twists, but we have a different lattice constant. So that also gives you the Moret pattern. And this is some zoomed image. And we also checked if the magnetization is still there, and is it out of plane or not. So for this, we used also in situ MOC to look at how the magnetization looks like. So from this, we can get the Curie temperature is around 60 Kelvin. But all the experiment that I'm going to show here is done at 300 millikelvin, so we don't need to worry about the paramagnetic or something temperature-related states. So again, as I mentioned, in order to enter the topological phase, you have to know where the chemical potential is, because that's one of the criteria you have to fulfill. Otherwise, you are not sure. So for example, in this triangular lattice, niobium diselenite, the topological phase occurs this high symmetry points where the Rashba goes to 0 that I mentioned. And these high symmetry points, you can look at it in this case as monolayer after you adding Rashba and Zeeman terms, and which is basically M points and the K and the gamma points. But in STM, because niobium diselenite is metal, so it's not easy to gate even. I mean, you cannot gate the metal basically. So we don't have a gating option. So we cannot move we cannot move the chemical potential. So what we are looking for, some high symmetry points that are close to the neutrality point, so we don't need to move, or a little bit do something, so we will very luckily end up in this place. So now, but luckily we are, and in the monolayer case, this point is still like 200 millielectron below the Fermi level. So that means you still need to dop to 200 millielectron volts to enter that region. But as I said, we are using bulk. In the bulk, you don't need to do much. You like around 50 or 100 millielectron below the Fermi level. So, but you still need to move this much. Okay, this value is also depend on how good your DFT is. So it's in this range. So before starting everything, the main thing we need to check is, do we have that shift? Because if you don't have that shift, then whatever you observe, it's not fulfilled the first criteria. So in order to check that, we look at the local STS spectra. So this is a niobium D band, which is above the Fermi level here. We cannot see much on this side. It's not that sensitive. But as you can see, if you look at this, follow this band, if you have a chromium bromide on top, but you are seeing through the D band, then there's a shift. And of course, this is the right way shift because everything is below. So in order to move this thing, this needs to be shifted this way. So you can also measure this shift precisely by looking at this kind of line cut spectroscopy and just following the D band. And from this, we can get roughly 80 millivolt shift. So this puts us roughly in this category. But I will tell you more about, in the end, this is not that much important. But for now, you just need to know we are in this region. Okay, now we can look at the low bias spectra. So basically, here is the tunneling spectra on the bare niobium diselenite. You have a superconducting gap. Then this is through the chromium bromide in here. This is normalized, so don't trust here. So, but the two spectra looks similar, but except there's an extra band inside the superconducting gap. So you can see it more clearly by subtracting that data from this. And then you end up in this type of plot, and here it's actual gap, but now I call it topological gap, but it's not proven yet. But in order to convince you, you have to look at the boundary of the sample. If this is really related to some kind of topological gap, then if I move from trivial to non-trivial, then this gap should close, or I should get some states there. So now this is this is the spectra taken on 3 different locations, and at the edge we have some enhancement of the density of states, and this exactly locates the gap edge of inside this, let's say this gap. And you can also look at how this state changes in space by mapping out at this particular energy. And as you can see, that's the topograph. This is the mapping of that local density of state at this energy. As you can see, this is mostly localized at the edge of the sample. And okay, it's STM, so you have many islands. You can look around in different islands, and you always see this states which is basically localized at the edge of the sample. Okay, so the first thing you think is, okay, is this states kind of trivial states, like for Kondo or some states which exist roughly around 0. So in order to eliminate that, you have to first answer, is this states related to superconductor? I mean, that's at least you have to check. So in order to do that, you need to first eliminate the superconductor from the picture. So for example, you just apply very high external magnetic field, 4 Tesla, out of plane in this case. If you do that, then you don't see anything. So the states disappears when you remove the superconductor from the system. And okay, this kind of tells you, okay, this states is not like standard age state, which is not related to superconductor, and it's also not related to Kondo effect, which usually happens if you have some magnetic moments that couples to the electron bath, and that gives you this zero bias states in the system. Okay, and then, okay, our colleagues also did some calculations here, and there's some comparison between experiment and the theory, and there's some numbers which matches from theory and experiment. But what I'm going to tell you now is what we cannot capture from this theoretical calculations, which is we also have, even if you have this age state, but we have also these modulations. So you have some certain modulations which is not really captured from this simple phenomenological model, and we try to understand why we have modulation. So the first thing you can think of is this, because we have this Moiré pattern here, is this Moiré pattern somehow plays rule, and this causes this type of modulations? If does, how can we understand this? So the first thing you can think, okay, little bit of background information about Moiré pattern, which is projection of one periodic pattern to another. And usually you can achieve this by twisting two lattices, or you just misalign two different lattice constants. This also gives you the Moiré pattern. So the first thing is the Moiré pattern creates this kind of periodic potential into the Princeton materials. And under this periodic potential and this lattice constant, you fold your bands to create new Boolean zones, new mini bands, the Moiré bands, and which is shown schematically here. And how we can apply this to the topological systems? So in order to understand this, let's go back to the one-dimensional case. Again, parabolic band. And as you can see, without the Moiré, usually your topological states lives on the bottom or top of the band, because over there you have this spin helical state. Now, if you turn on the Moiré potential, this potential can be modulation of exchange coupling between superconductor or ferromagnet, or electrostatic, just electrostatic potential, because you are using two different layers. Now, if you turn it on, then now you can see you have many different regions where you can have topological states. And you can see this more clearly if you look at this type of plot, this type of phase diagrams. And this is what happens without the Moiré. When you increase the Moiré pattern, you can see you create new states inside the non-trivial states where you have without the Moiré. So this really creates, the Moiré pattern creates new trivial states in the absence of, which you cannot see it, absence of Moiré. So it's only the Moiré pattern creates this new states. And you can simply extend this to two-dimensional, again, high symmetry points, especially what we are looking at close to the neutrality points. And without the Moiré, you don't have anything. Now, if you turn on the Moiré, you create this new topological region where it only appears when you apply Moiré. So now the question is, okay, this is theory. Now how we can detect an experiment? So the first thing you can look at is there any electrostatic or potential difference you can check this by following the conduction band of the chromium bromide, and this it is taken along this Moiré pattern here, and this is the energy, and this energy modulates exactly as a function of the Moiré, period of the Moiré pattern. And you can see them more clearly in this two-dimensional image here. This is topographic image. This is taken on maps, local density maps on one energy. This is another energy. From this you can see this bright region becomes dark and dark region becomes bright. And that gives you, basically, you have a modulation of around 50 millielectron volt in this system. Okay, now so now let's look at what happens around superconducting gap. So here what I'm doing here is I'm sweeping the bias from this energy to here and looking at the map. So as you can see, if I hit certain energy in here somewhere on both sides, I see the pattern. And nowhere else I see the other pattern. So it's outside or inside here or not. It's only certain energy I can see this Moiré pattern. So what does it mean? So in order to see this, let's do some energy cuts. And here, this is maps, which is this taken on this particular energy at this energies, for example. So you only see this modulation close to I said before, the edge of the topological gap, which I mentioned before, and nowhere else. Outside or inside, only this energy, around this energy, let's say. So this, our colleagues, Jose Lada, simulate this by just modulating the exchange coupling between the superconductor Cooper pair and the ferromagnet. So this is how you just modulate the exchange interaction, and then you look at the local density of states, how it changes. So here, again, when you hit that gap edge, you have very localized local density of states, which modulates as a periodicity of the Moiré. But if you hit outside or inside, you have very delocalized states, which is similar to the one I showed here. Okay, it turns out this also affects on the edge state. So here again, there's some topographic image. And here, these triangles just indicates the periodic Moiré patterns. And then again, if you are inside, probably you can see slightly, there's a modulation inside. Now, if you hit if you map at the edge mode, you can see this modulation is actually, it matches with the modulation of the Moiré. And you can also do the calculations to reproduce these results. And of course, one of the questions, okay, you have a very large states in intensity here, but lower intensity there. But if you look at carefully, okay, you have a large intensity on the large point, but you still have some intensity even on the darker region here. And this tells us, okay, the Moiré pattern also very important to create. It helps you to create more topological regions that you only see it when you have a Moiré pattern in the system. Okay, with that, it's the end of my talk. So the most of the experiment is done at Aalto in the Professor Peter Lillerath during my postdoc, and we also benefited from Sebastian Van Dijken's group, some magnetic measurements, and the first part of the series is done Timo Ojanen, and the second Moiré part is done by Jose Lada, and we also nice collaboration with Adam Foster's group for some DFT calculations, and this is our funding agency. So that's, thank you very much.